Okay, yeah, you can get going. Let's not waste time.
Okay. So I will try to make it short because we lost some time already. So let's see. All right. So I'll do this. Oops.
Yeah, this is the first time. This first time that the timing was was totally screwed up. Yeah, I'm sorry. I'm sorry about
no,
it.
that's
Yeah.
okay. That's okay. So okay. So thank you. First of all, thank you so much for having me. It's a pleasure. What I'm going to report today is our recent work that indicates the existence of chiral orbital currents, or just simply loop currents. And then these loop currents dictate the very unusual quantum states that shows a range of very unusual properties. So these properties will be reported in this talk. So as one thing I want to emphasize is that this is the work that is very new. As you can see, this work was just published, and actually print issue was about to be published. So it's interesting work, but then there are still many questions remain unanswered. Okay, so I hope this discussion could generate more discussions in order to better understand the phenomenon that I'm going to show you. So so this is a material. This materials involves involves magnetoresistance as well as loop currents. So I will give you very brief review of this magnetoresistance and loop currents. This is my first time join this seminar. So, but then I assume a diverse audience of scientists. So I'll just give you a couple of slides of magnetoresistance and loop currents, emphasizing why the work that I'm going to report is different. And then after that, I will again briefly introduce control of quantum states using very small DC currents. And this is something that we have developed in recent years. And then this DC current control can be very effective for certain type of materials. And then the materials in question, manganese 3, silicon 2, tellurium 6 is one of them. So I will report that that part of results. So causal magnetoresistance, this is something that is very popular, at least in 90s, last century and the early this century. So causal magnetoresistance is extraordinary enhancement of electric conductivity in the presence of magnetic field. So this is the cartoon. I lifted from a paper just showing that for insulating materials without magnetic field, there's not much current can go through. With magnetic field, then there more charges or electrons can go through the materials. So in this process, the essential elements is a spin-dependent scattering. So magnetoresistance conventionally is associated with a field-induced spin polarization that drastically reduces the spin scattering and therefore electric resistance. So if you look at this cartoon based on two-channel model, you can see that if the spins are not aligned or polarized, we have more scatterings. But then if the system is better aligned or polarized, we have a less scattering, therefore we have a smaller resistance. Okay, and the conventional causal magnetoresistance normally happens in the whole doped manganese. Okay, for example, this compound, this compound. So key elements in this is that in these materials there is mixed valence states. So in other words, we have a manganese 3+ and manganese 4+. So this mixed valence states enabled double exchange, and then this double exchange controls magnetic properties. And then the other important elements is the Young-Taylor distortion, and this distortion actually dictates the transport properties. Of course, in these arguments we have more. For example, phase separation and so on and so forth. But these are the two important elements of in the causal magnetoresistance. And oops, what is it? Why is it not moving? Okay. And then, so this is one of the well-known papers that was published in the late 90s. So you can see that the resistivity, this is resistivity as a function of temperature. So without magnetic field, it is insulating. With magnetic field, say for example 7 Tesla, and then the system has this several orders of magnitude drop in resistivity, and it becomes metal. But the important thing, the important things that I want to emphasize here is that when the system becomes metal, the spin here we have a fully polarized spin states. Okay, so this is one of the example, and also in 90s there is another system which is this 227 system, thallium manganese 227. And in this system, there is no mixed valence state, and yet there is still Colossal magnetoresistance reported. So this is one of the figures I copied from this paper. But then again, in this system, it also requires the fully polarized state in order to have this Colossal magnetoresistance. Of course, there is a detailed argument that this type of Colossal magnetoresistance is driven by magnetopolarons along with low-density electron gas interacting with the spins. But then the point here is this, is that the magnetic polarization is essential for all conventional Colossal magnetoresistance, okay? And then the other important elements in my talk is loop currents, or we call it the chiral orbital currents. And so this was initially proposed by Chandra Varma to address the cuprates, superconductors. And then this is the cartoon picture. I copied it from one of these papers. So basically what happens is that these loop currents circulate coherently between copper and oxygen orbitals, and it generates the orbital moments that are indicated by these arrows. Okay. And so this is the starting of this discussion of loop currents that may exist in cuprates, and then later on people extended these concepts to other materials, for example, iridates, and then there is several papers reporting the existence of orbital moments due to the loop currents. Okay, so that, and then more recently, there is a large number of papers reporting the chiral charge order in the Kagami superconductors, and I think the Rice group is among one of these groups recently reporting this phenomenon. And then other type of materials is twisted bilayer graphene, and then there again people reporting orbital ferromagnetic properties in that systems. So the point here is that the chiral orbital currents may be widespread beyond the aforementioned materials. But then I want to emphasize is that no microscopic transport phenomenon associated with loop currents that coexist with long-range magnetic order have been reported. So here we report the first such case. So that is the loop current-driven Colossal magnetoresistance in the ferrimagnetic materials of this compound. Okay, and we use a small DC current as a stimulus to control the loop current state. So loop current, this AC current as we use this as a small perturbation started a few years ago. So this is the very first paper that we reported, that we use very small current to control the iridates, this compound. So what happens there is that when you apply small current there, you can actually modify crystal structures and then therefore magnetic properties and the transport properties. So this is our very first work, indicating that the small current as a small perturbation actually is very effective for certain type of materials. So there is two essential conditions for us to effectively control structures and phases. That is, one, strong magneto-elastic coupling and spin orbit interactions. Okay, so we have to have that. And then the second is that we have to have distorted crystal structures or canted magnetic structures. And so this picture indicating the technique that we developed in recent years. That is, we apply small current to where we are doing single crystal X-ray diffraction. So in other words, we could measure lattice parameters as a function of current as well as temperature. Okay, this is the temperature control device. So we use this technique to a range of materials, including oxides and carcagenides. And so this is these are the recent work related to the electrical control, the current control properties. So this is what, when we talk about the current control, one thing that I have to emphasize, that's a heating, okay, self-heating or dual heating. This is something that is very essential. So we are particularly mindful that the dual heating could cause spurious behavior. So we have these bad examples in this community. So we are extremely careful in terms of monitoring and addressing the dual heating, if any. We want to make sure that everything that we've seen is intrinsic. The other thing, the point that I want to make is that the current control is different from electric field effects. And then this is actually reported in late 30s by Franco or Paul. So we call it the Paul-Franco emission. That is very different. That requires high electric field to mobilize trapped electrons in insulating wells, well, in potential wells. So you will see the difference there as we in a minute. So this is the title of the work that involves colossal magnetoresistance, that involves small current control of the quantum states. So this work actually involves a number of very unusual properties. So let me first summarize this here. Then we talk about the details. So one of the items here is that this colossal magnetoresistance, occurs only when magnetic polarization is avoided. Okay, so this is one of the important feature of this material. The second one is that this colossal magnetoresistance is actually very sensitive to small applied currents. This is something that we do not see before. The first item, that the colossal magnetoresistance only happens without magnetic polarization, actually happened in other materials. For example, calcium-3, ruthenium-2, oxygen-7. But then the colossal magnetoresistance that being sensitive to small current is something that we've never seen before, at least to my best knowledge. And then the other thing is that we have seen anomalous IV characteristic, and then including Josephson-like effect. And then this is not superconducting materials. This is actually very insulating materials. And yet we see very robust Josephson-like effect. And then there's another, there is a bistable switching. This bistable switching is time dependent. And then it is always first order switching. And then this switching very often takes seconds or minutes to occur, and then depends on orientation of applied magnetic fields. So these are the few things that I want to highlight. So these are the things that's very striking, and some of them are still very puzzling. So let's look at the structure of these materials. And this materials is not new. It's been known for more than 30 years, and first reported by this paper in 1986. It has two inequivalent manganese sides. We call it Mn1 and Mn2, and then that forming a trimer honeycomb lattice. Okay. One thing that I want to point out is that here the valence state is 2+. That means we have 5 3D electrons. So in this case, we should expect orbital moment to be 0, L equals 0. So in other words, we should not expect very large spin orbit interactions. Okay, so so these are the basics of this material, and this is the structure, and this is two different manganese sites. This is the honeycomb lattice, and also our recent data indicating that the below Curie temperature there is no structure change. Okay, so this is the diffraction pattern at the 50 Kelvin. And the magnetic structure of this material, this is very magnetic, and Tc is 78 Kelvin. The recent neutron data by Ye Feng, this paper was just published a couple of weeks ago, indicating that the structure is non-collinear, right? But mostly the spins are actually lies within the AB plane. So the A-axis is actually magnetic, easy axis, whereas C-axis is magnetic, hard axis. Okay. So then work reporting the behavior of this material is actually reported in this PRB paper in 2021. So in that work, we are reporting that the resistivity as a function of temperature here is that when we apply small current, here is 10 nanometers, amps, and with a magnetic field applied along C-axis, which is hard axis. So we see the drastic resistivity drop, especially at the 14 Tesla. So from here to here, the resistivity drop is more than 7 orders of magnitude without spin polarization. Okay, and then the other piece of evidence here is this: is that let's look at this dashed line first. So this is an isothermal magnetization that we measured at the 10 Kelvin. So the red dashed line indicating easy axis magnetization. So you can see that the easy axis magnetization saturates at a very small field, a fraction of 1 Tesla. And then C-axis magnetization takes a long time to saturate. So this blue dashed line is a C-axis magnetization. So you can see even at the 14 Tesla, the absolute value of this is still smaller than the value of magnetization for C-axis. But then if you look at the resistivity, which is again, this is solid lines. So the red lines indicating the magnetic field along the easy axis, the drop is only 20% at most, okay, the resistivity drop. Whereas if you look at the C-axis, which is hard axis, the resistivity drops about this 7 orders of magnitude. So what's important here is that the resistivity, this 7 order, the drop in resistivity actually happens when magnetic field is larger than 4 Tesla here. So in other words, this happens very quickly for the system to become metallic.
So which direction is the current?
AB plane. So A-axis here.
Okay.
A. Okay. C-axis has similar effect, but smaller. Okay. And then this work is also confirmed. This results confirmed by another group that they published the results in Nature. So the other important feature that I want to point out is the anisotropy. As we said earlier, that the L equals 0 for this ion. Okay, so we should not expect very large the spin orbital interactions. Yes, therefore magnetic anisotropy. And yet here in this polar plot, which we can see the transport properties actually is very anisotropic. So this is a hard axis this is the configuration. This is the relationship between the magnetic field and the C-axis. So when theta equals 0, then we say field is parallel to C-axis, hard axis. So in this case, we have small resistance. But when magnetic field or when theta becomes 90 degrees, which is here, you can see resistance is much larger. So here this polar plots indicating a very strong anisotropic transport properties. Okay, so anisotropy, the anisotropy field is more than 13 Tesla. So this is again is very unusual, given L should be 0 for this manganese 2+ ions. So these are the early results that we have seen, and then this is Yefeng's work. So after our first paper on these materials, so we are wondering what happens to the spins due to the manganese spins, manganese electrons. So then Yefeng did that work. So this is early data of this paper. So this is the purple line is the resistivity, and then this blue line is the C-axis magnetization, and here the field is parallel to C-axis, and then on this right-hand scale it is a theta. That is the canting angle, reflecting the change of the spin with the changing of magnetic field. So you can see that this is early data. Theta changes very slowly. So in other words, this theta changes as a function of the field is almost consistent with the changes of the magnetization around the C-axis. But then also in this figure we can see, but then the resistivity here showing completely different field dependence. So for resistivity, when the field is higher than 4 Tesla, the system is already in metallic states. Okay, so this is early data. And then this more recent data, which actually applied the magnetic field up to 14 Tesla. And then this indicating that indeed, that the spin actually changes very slowly. That is inconsistent with the changes of the resistivity in the magnetic field. So here we say spin rotates only gradually with the field applied along parallel to C-axis. This is inconsistent with rapid occurrence of colossal magnetoresistance when magnetic field is applied along the C-axis, the same direction. And then there is the detail here, which is important. That is, in this paper, it also reports the magnetic moment. So for this ion, the magnetic moment ideally should be 5 Bohr magneton. But then for this two different magnet sites, one of them showing 4.5 Bohr magneton, the other is a 4.2 magneton. Okay, so this is an early indication indicating that there may be some partial cancellation due to orbital moment generated by loop currents. So this is our proposal. So the proposal, so that is loop currents could exist in these materials, and that the loop currents can be in any directions, but the majority or dominant loop currents should be in the AB plane, which is this. Okay, we use different color to indicating different loop currents, to indicating different magnitude of the currents, of loop currents. So this loop currents naturally generates C-axis orbital moments. Okay, so this is an important assumption, and also is consistent with our later discussions. So loop currents that here we consider is mostly in AB plane. So it's AB plane loop currents flowing along the edges of manganese and the tellurium octahedra. And then so therefore that generates the orbital moment that along the C-axis. So this is one of the important proposals that we proposed in our work. So then why loop currents can generate, or the control loop currents can generate the magnetoresistance? So this is again is the cartoon picture here. So let's see, we have loop currents in the systems, and this loop currents the circulation of loop currents can be in any directions. So for example, in the AB plane, it can circulate counterclockwise or clockwise when magnetic field is 0. Okay, and then this loop currents actually generates domains. And then in this case, without magnetic field, it generates disordered domain that certainly generates scattering. So therefore, high resistance. But then if you apply magnetic field to the system along C-axis, and then this magnetic field along C-axis will coupled with the C-axis orbital moment. That will actually favor one type of domain. In other words, one domain with domains with one circulation direction, whereas the group currents with other directions will gradually diminish or eventually vanishes. So when magnetic field is higher. So this, as a result, generates one single domain that consists of all the loop currents with same circulation direction. So therefore, reduces the scattering, therefore, reduces electric resistance. Okay, so this is of course is something that we cannot directly measure. Okay, but then there is some strong indication this argument is consistent with the experiments. So let's look at the current. Okay, so without current, okay, so without magnetic field, we measure the resistance with different currents, small currents. So this is a very busy picture. So let's look at this area. Okay, so this area you can see that if we apply current that is 10 nanoamps, so resistance is very high. Is here. But then if we gradually increase current, for example, here is 10 micron or milliamps and so on, and then resistivity drops, and then more importantly, this transition temperature changes. So if we look at here at the 10 micron, here we have this second order transition corresponding to the Curie temperature at about the 78 Kelvin. But then if the current is increased to 1 milliamps, then this transition is suppressed to lower temperatures, but it remains second order transition. But then when you slightly increase current from 1 to 1.5 milliamps, then we started to see this first order transition. Okay, when you further slightly increase the current to 1.8 milliamps, and then this first order transition becomes even more obvious. And then so the TC is dropped to the lower temperature, and then also the second order transition becomes first order transition. But then as you further increase the current, for example, 2 milliamps, then all this first order transition is gone. We measured this resistivity simultaneously with magnetization. So this magnetization is showing exactly the same thing. So when the current is 0, we have this transition around the Curie temperature. But then as we increase the current, the TC drops. And then at 1.5, we have this first order transition in magnetization. And then when the current is 1.8 milliamps, it is even stronger, showing stronger first order transition at the lower temperatures. And then when you further increase the current to 2 milliamps, then there's no longer long range order. So then this is when the field is 0. Okay. So then if we apply magnetic field and also changing current, so what do we see here is this. So the currents, the effect of magnetic field along C-axis actually is opposite. It's trying to pull the transition back to the higher temperatures. So see, current is suppressed TC, whereas the magnetic field along C-axis actually is trying to enhance TC. So from here to here, we still see colossal magnetoresistance. But then what's interesting here is that when the current is higher than 2 milliamps, for example, 5 milliamps, we do not see colossal magnetoresistance anymore. So in other words, it is gone. Okay, so this colossal resistance is extremely sensitive to small currents. So for this particular case and sample, it is when the current is stronger than 2 milliamps, we do not see colossal magnetoresistance anymore. So this is a unique feature of this material. And so this is the phase diagram indicating that there is this strong correlation between between Curie temperature or long-range water and the colossal magnetoresistance. So in other words, colossal magnetoresistance is not determined by by manganese spin alone, but then certainly is strongly related to the colossal magnetoresistance. So this indicating, so this is the resistivity ratio as a function of current. So when the current is higher than 2 milliamps, we do not have this colossal magnetoresistance. And similarly, that when the current is larger than 2 milliamps, we do not see long-range water anymore. Okay, so this is the point of this plot. So I also mentioned earlier, this is related, but then this is the IV characteristic is another aspect of the transport properties. So we also measure that. So we have this very unusual IV curves. Okay, so again, let's look at this. This is a zoom in picture. So we have this, we have this, this is certainly, it does not follow Ohm's law. When current is very small, it does follow Ohm's law, but when current is slightly higher, then we see this, turning point. This is, we call it this negative differential resistance. And as we further increase current, and so at the point, I say at the critical current C here, and then the voltage jumps in the first order manner to much higher voltage. And then another turning point, continue on that this negative differential resistance. So this is one way magnetic field is zero, okay? And this type of behavior actually persists up to 70 Kelvin. But then if we apply magnetic field, again, apply magnetic field along C-axis. So what happens is that is this, let's look at this picture here. So this first turning point becomes vertical here. So this is at the 3 Tesla. But then as we further increase magnetic field, for example, 14 Tesla or 7 Tesla even, then this becomes completely vertical line. So this indicating that delta V and over delta I is almost zero. You know, this is a Josephson junction effect, a Josephson effect. But then we know that in this system, we do not have superconducting component. They are all insulated. So this again is something remains puzzling. And then we also measured. Then this is a long story, but then our study, actually we studied this for over years. So our study indicating that this materials may have some time dependence. So what we did is that we measured voltage as a function of time. So this is the set of data without magnetic field. So if we apply current, for example, 2.030 milliamps, nothing going on. Well, in the initial time, it has this slight drop, and then it's stabilized and going on, nothing happens. But if you apply current slightly from 2.030 to 2.035 milliamps, then all of a sudden, near 10 seconds, there is a voltage jump. Well, it spikes here and then immediately settle down here. And then as you further increase current slightly, this delay time becomes shorter. But then they all end up in this area. Okay, so that's why we call it the bistable switching. They only have 2 states, either here or here. Okay, so this is one magnetic field is 0. So then again, we apply magnetic field. So when we apply magnetic field here, so for example, 7 Tesla, then this delay becomes even longer. So this is 10 seconds, and whereas here is almost 2 minutes. Okay, so this again is that the change is also very subtle here. So it's a 3.97 milliamps, nothing happens. But then if it is a 3.98, all of a sudden we have a jump. This jump is more than 2,000% jump. And again, it's stabilized here. So as we further increase current, the delay time becomes shorter, but then again, they all end up here. Because that's why we call it the first order bistable switching. Okay, the switching gets strengthened when we apply magnetic field along z-axis. So this is the cartoon illustrating the reason that why this is strengthened, that we believe that this magnetic field actually coupled with this orbital current or orbital moment that strengthens this loop current state. So naturally, we want to see what happens when we apply field along this a-axis, that is this direction, z-axis. So then what we see here is that this bistable switching state is gone. Okay, the system becomes more normal. So of course, there's still this upturns. That means there may be a mixed state between this and this, but in general, the behavior becomes more normal, I would say. So the voltage changes with the size of the current. So there's no longer this bistable switching. So we believe that this bistable switching is probably similar to the melting transition from solid to liquid, or simply from ice to water. So when ice is melting, all the thermal energy is trying to break all these hydrogen bonds, then without changing temperature. So the temperature changes only when all the hydrogen bonds were broken. So then temperature changes. Here, well, our argument is that all these external currents maybe is breaking this internal loop currents, but then this current stays at this low voltage states because there is still some loop currents that are still remaining. So when when all the loop currents were broken by this external currents, then all of a sudden the voltage jumps from the low voltage states to the high voltage states.
So have you done X-ray measurement indicating what happened to the crystal structure when this happened?
Our temperature is 80 Kelvin. The X-ray diffraction so stops at 80 Kelvin.
So this cannot be done. Okay.
So yeah, we cannot see that. So now a group at Oak Ridge is doing STM for us at low temperature applied currents. So hopefully we could have.
Phone can apply a current and do neutron scattering, right, to see what happens. Yeah.
Yeah, he could. Yeah, he could do that. Yes.
Okay.
And then some related to this is magnetostriction as a function of field. So you can see that when magnetic field is parallel to c-axis, a-axis, the unit cell expand. Okay, so this blue lines indicating the change or expansion of a-axis. Whereas for when the magnetic field is applied along a-axis, the a-axis does not change much. Okay, so this this again is consistent with our the following up work here. That is, we dope the system. So if we slightly dope, not slightly, if you dope the system with germanium to replace silicon, here the unit cell expands. But then if we if we set the dope selenium to replace tellurium, the unit cell shrinks. So then if you look at the resistivity here, the germanium dope sample where we have expanded unit cell actually having even larger magnetoresistance. So this time it's 9 orders of magnitude drop in resistivity. But then for the selenium doping, where the unit cell shrinks, the magnetoresistance actually the effect becomes much smaller. And then you measure magnetization. Here you can see that actually germanium has much smaller the magnetization or saturation moment, whereas the selenium, which shows much weaker causal magnetoresistance, having larger saturation moments. And the recent neutron data actually is consistent with this observation So that is the moment of selenium or gadolinium doped samples, which is this. Actually, the moment actually becomes much smaller. Okay, so for the pure sample, it is 4.5, 4.2. For the doped sample, germanium is a 3.6, 7 or 3.3. So moment gets smaller. So this is another indication that when you see larger Colossal magnetoresistance, there is a larger cancellation. That is an indication that the loop currents get stronger because the cancellation gets larger is because the c-axis orbital moment gets bigger. Okay, so again, this is our argument. We do not have direct evidence or observation indicating that. So according to Feng Ye and the other experts, there is no way that we can distinguish the static moments and the orbital moment induced by loop currents. So with that, I finish my my talk. So these are the few important features of these materials, and most importantly, these are the unsung heroes who did the work. Okay, thank you.
Yeah, thanks a lot, Gang. Yeah, I'm sorry again. This is very interesting, very interesting materials. Yeah. So, okay, and any questions? And if not, I can try to. Yeah. So I guess the key question is that I guess this the loop currents, as far as I can see, is still kind of a speculation, right? it's all
the loop currents. I mean,
everything is speculation.
Papers,
everything is speculation.
Yeah. So, but then yes, this is certainly. But then this may be a reasonable one. We are suggesting maybe Kerr effect could help us identify the existence of loop currents. But then in all these measurements that especially when this materials is so sensitive to current, so this actually is a strong indication that maybe there is the loop currents going on in there.
So how do you guarantee the current you're passing through is homogeneous? And I mean, people have known for a long time, right? When you have a current passing some of these materials, it becomes inhomogeneous.
Well, if it is all inhomogeneous, you don't see this type of first order transition.
Really? I mean, I thought that would work.
Yeah, because see, inhomogeneous. Well, let's see. Maybe this is not exactly right. Yeah, I cannot say that we have a clear evidence that we can rule out this, but then the sensitivity to the orientation of magnetic field, for example, this is a strong indication that the loop currents may be something reasonable to explain all this.
No, I mean, I like the story. Don't get me wrong.
No. I do think this, because the reason that I repeatedly said this is a proposal, it's not experimental observation, is because there's no way that I can observe this. Yeah.
But are there any anisotropy in transport measurement when you have when you put a c-axis field?
Yes, very strong. Very strong.
You have a c-axis field, yeah.
Yeah, it's very strong. Yes, there is similar effect, but the effect is weaker. Yeah, and then all these data are actually in the supplemental materials in the paper. So yeah, it's
Koji has a question. Yeah, he actually Koji might be able to shed some light. Yeah, Koji can look at the
Hi, Gang. This is
Hey, who is this?
Yeah, I'm actually at Austin, not in Houston, but I saw your talk, so I just attended. Yeah, wonderful talk. Yeah, beautiful results. Just curious, do you see strong hysteresis, both in your current magnetic field and all those? So that might indicate you have a lot of domains that are going on in this material.
Hysteresis in terms of what? In terms of applied field?
Let's say field, right? Field or current. You just back and forth.
Okay. Yeah. If you just measure resistivity, there is no hysteresis. Okay. If you measure magnetization, isothermal magnetization, there are not a whole lot. There is no hysteresis. Okay.
That's very strange.
But yes, but if you so this is the data that's still going on. I didn't put it here. Is that if you measure IV curve. Okay, so the IV curve I showed here is that we apply current and measure voltage. So now what we are doing is that we apply voltage to measure current. Then we see a very large hysteresis in terms of the IV curve. So it's just like a switch, like a device, for memory device. So that is actually very, that hysteresis effect is very strong, which is in good way, very strong.
Right. Yeah, I might just send you an email and talk more about some details.
Yeah, I think he can make, because he can potentially measure, metal insular transition and determine whether it's really samples homogeneous or not, right?
Yeah, absolutely. Yeah, wonderful. Yeah, thank you.
Okay. Sure. Thank you.
Yeah, so there's a question online. Oh, Hugo, do you have a question?
Yeah, I had actually the same question, but the answer is there. So it looks like an orbital ordering transition, which is broken down by the current. And so one would expect a strong hysteresis back and forth when you measure the IV curve. And so the answer is there.
Oh, IV curve is this. Okay. So IV curve, if the way that I'm showing here, apply current measuring voltage, the hysteresis effect is very small, very small. But if you use AC current, then there is a strong hysteresis. But then if you turn around, you use voltage as a source and the measuring current, then that hysteresis is very strong.
As I say, I mean, it looks like basically a breakdown of the orbital order, the electrical breakdown.
Yeah.
So you have an orbital order that develops, and then you break it down by applying voltage.
Well, there shouldn't be any orbital order, right? He argued. I mean, it shouldn't be any orbital order, strictly speaking, right?
Well, that can be measured, by the way. You can just you have to do diffraction with electrical field applied, right?
This current, we assume, is extended to multiple unit cell, right? So the reason that it changes takes so long is because you have to adjust all the atoms. So in other words, the time scale is set by the atoms or tellurium atoms or bonds, rather than setting by electrons or spins. So that might be one of the reasons that it takes so long for the system to do switch. So normally, this delay normally is picoseconds, right, or smaller than that. But then here, this is so long. So
I think this indicates that there is an orbital order, and you can actually detect it by displacement of the atoms if you do the diffraction in electric field.
In the electrical current.
Well, with voltage applied, basically sweeping through, so you would see the displacement of atoms. I would imagine a situation to me is not dissimilar to iron telluride. Actually, it has exactly the same sort of an orbital ordering, which can be broken down by field or.
I'm not suggesting this is similar to.
No. I'm suggesting. I think this is similar conceptually.
Yes.
Okay. So there's also a question online. Why do the orbital current occur at the same transition temperature as the ordering of the manganese moment?
Yeah, that is again is our argument. That is the reason that we have the large anisotropy is because of this very unusual orbital, which is generated by the loop currents, and the spin, which is due to manganese. So there is a strong coupling between manganese spins and the orbital moment due to loop currents. So these two moments actually are coupled. So if one of them is gone, and then then the others will be gone too. So that's why the Curie long range order here is actually important.
I think STM measurement will really. STM measurement will really shed a lot of light. You can put a current through and then do STM to see whether metal insulator transition. Because
Anping is doing that. The challenge here is that this materials is not two-dimensional materials.
Oh, so, cannot cleave.
Yeah, cleaving is very difficult. Yeah, but then they are still trying.
Okay.
Yeah.
Yeah, it's a very, very interesting material. I'm totally surprised.
Yeah.
Any other questions? Okay, Miss Gray.
Okay, so
Miss Gray, yeah.
Hi, can you hear me?
Yeah.
Yes, yes,
okay.
I can.
So first, thank you for the very interesting talk. So you mentioned that Kerr effect might be able to see the orbital ordering.
Yeah,
no,
this is a
no,
yes.
Not in this. I doubt. I mean, because there's so much background from manganese, right? I mean, I'm not an expert on Kerr effect, but the manganese background will overwhelm anything the Kerr.
Yeah, we in our paper in the last paragraph we cited a couple of reference. Based on that reference, we proposed that. So there is a more detailed theoretical discussion in that. But then so far, no one, well, to my knowledge, no one is doing Kerr effect measurements on these materials yet. But then certainly, this is one of the proposals that probably could help us identify the existence of the loop currents.
Could you also do second harmonic generation to see the distortion of the atom when you apply current?
Oh yeah, that certainly will help.
That's actually doable.
Yes, that will be very helpful. Yes.
Yeah, that's really doable. I mean, I think just get phone to do some diffraction under current on his machine. That's really will really solve a lot of problems. Yeah.
Yeah.
Cool. Thank you.
Sure. Thank you.
Any other question for Gang? Yeah, this is a wonderful material. Yeah, it's very interesting. Yeah. Have people done inelastic? Yeah, Igor, yeah.
Yeah, may just, I mean, I'm a bit concerned about this loop current terminology. I discussed it with Voma some time ago. I mean, loop currents are just a sort of a pictorial way to visualize unquenched orbital moment.
That's his fault. That's his fault. Okay.
I mean, just think about it. I mean, there are no real loop currents. It's just you can invent all sorts of loop current in order to represent what is a physical reality, which is an unquenched orbital moment, right?
Yes. So what is the proper terminology for this?
Well, I would think it's an unquenched orbital moment, and you have an ordering of the unquenched orbital angular moment, right?
Okay. All right. I'll keep this in mind.
No, but loop currents is a nice sort of pictorial way.
Nice story. Yeah. But it has never been confirmed though. I mean, I don't think. Yeah. Very controversial. Yeah.
Well, I mean, as I say, in principle, it's a way to represent the physical reality, which is this unquenched orbital moments, right? Because usually they are quenched, and so they don't have direction. But here you do have directions, which are represented as orbital currents. Anyway, it's a very fascinating story. Yeah, thanks a lot.
Thank you.
Yeah, very interesting.
Yeah, thank you.
Yeah. Okay. Yeah. Okay. If there are no more questions, yeah. Thank you, Gang. Yeah.
Thank you so much. It's a pleasure.
For mess up this. Yeah. Okay.
Yeah, it's a pleasure. Okay. Thank you. Yeah. Bye.